Using the function S is equal to S of T comma P, derive the expression for the heat given off during an isothermal compression. Now, how can we solve this question? What do you think will be the first step that we need to take? So the first thing I'm going to do, I'm going to take out the parameters which were given to us. We have the entropy as a function of temperature as well as the pressure. Next up, I'm going to find out the total derivative of the entropy. That will be written as ds. And I'm actually going to get it by differentiating t partially with respect, well, that is differentiating s rather, partially with respect to t. That will be added to the partial derivative of s with respect to p. Now, if I differentiate that with respect to t, I would keep p constant. And if I differentiated the entropy with respect to P, I'm going to keep the temperature constant. So this is what I mean. This is going to be partial S, partial T, at constant P. And this should be multiplied with the natural derivative of the temperature. So this is going to be added to the partial derivative of the entropy with respect to P. And in this case, we're going to keep the T, which is the temperature, constant. That should be multiplied with the natural derivative of P. So let us call this equation 1. Now we know that for an isothermal process, whether it be a compression or an expansion, you would always have dt to be equal to 0. So that is actually going to affect this first part of the right hand side of that equation. Now in that case, ds is going to be equal to partial s, partial p at constant t, and that will be multiplied by the natural derivative of the pressure. So let us call this equation 2. Now, I'm just going to write it here. This is ds, and that is equal to partial s, partial p with respect to t multiplied by the natural derivative of p. Now we know that the change in the heat that is given off within or present within during an expression or a reaction, that is actually given as TDS. Now we know this is ds. So what is going to happen? We will take ds, which is given as this, and substitute it into this. So this is what we're going to have. This will be T multiplied by partial S, partial P at constant T with respect to the natural derivative of the pressure. So we should have, wipe all these out. We're going to have dq, and that will be equal to T multiplied by partial S, partial P with respect to T, well, at constant T rather, multiplied by the natural derivative of the pressure. Now, let us say this is the third equation, that is equation 3. Next up, we know that the entropy or the total entropy of a reaction or a process is equal to the standard or entropy minus nr multiplied by natural logarithm of the pressure. Now, what if we wanted to find the partial derivative of the entropy with respect to pressure at constant temperature? Now, we purposefully want to do that because we actually want to find this stuff. So that will be ds dp, and right now that is going to be at constant t. This is actually a constant, so differentiating this would give us a 0. So we're going to have a negative nr, and we need to differentiate ln p with respect to p at constant t. That would give us 1 over p. So this is going to be negative nr divided by p. So what that means is we have partial S partial P at constant T. That is equal to minus nR divided by P. Now we already have that stuff in equation 3. So what I'm going to do, I would actually change this form and replace it with this other form in equation 3. So we have dq, and dq is equal to T multiplied by minus nR divided by P, and this is multiplied by dP. Now we know this is our constant T. We don't really need to write that no more because we already have the constant T represented on this other side. So I'm going to wipe this stuff out also. Now the next thing we need to do, we need to integrate both sides of this equation. Now we need to integrate that. This is dq. On this other side, I'm going to integrate it at the upper limit of P2 and the lower limit of P1. So this is T multiplied by negative nR divided by P multiplied by dP. So I'm going to wipe this out also. Now if I integrated a differential, that would change from that differential form into the natural or real form. Now we have T over here and negative nR to be as constant. So I'm just going to take them out. That will be minus nRT. And then I'm going to have integral P2, which is the upper limit, and P1. And that is 1 over P dP. So we need to work this. Now this should come off pretty simple in it. We know that the integral of 1 over P is going to give us ln P. So this is going to be Q is equal to negative nR. So I need to rewrite that. Negative nRT ln P. Now this is going to be at the upper limit of P2 and the lower limit of P1. So what does that mean really? Let us write it over here. This is nRT. And here you're going to have ln P2. What did I actually do? Now how to work this, you need to take the upper limit and substitute this variable, which is the P, as the upper limit. So that is going to be ln P2. And now you would subtract ln P1 from that. Now what did I do over here? I just took the P1 and substituted it for P in the second case. And that answer, I need to subtract it from this first. So that is the reason why I have this. Okay? So this is going to be Q. And Q will be equal to negative nRT ln. Now we have ln P2 minus ln P1. From the laws of logarithm, you could actually change this, and this would give us P2 divided by P1. So this is actually going to be the equation for the heat given off during an isothermal compression. If you had it to be an isothermal expansion, that would have given you a positive. But we have a negative here because that would give us some heat. So some heat would actually be lost, and this form would actually be formed. So this is the answer.